another way of forming new sets from old ones. It's something like crossing one set with another. With two sets, this seems pretty straightforward. The Cartesian product of two sets, A cross B, is the set of all ordered pairs, A comma B, for which A is an element of the set A and B is an element of the set B. So formally, it looks like this. So our goal for this video is to extend this definition to an arbitrary number of sets, so we can cross any number of sets. So there's a couple of difficulties that we have to deal with right off the bat. First, notice that there's something very different about this definition from how we normally think about an ordered pair. We usually think of Cartesian coordinates and ordered pairs as points in 2D space. It's just a grid with the real numbers on the x-axis and real numbers on the y-axis. But the concept of a Cartesian product is actually way more abstract than that. You can make a Cartesian product out of any two sets. They don't have to be the same set, like R cross R. I'm focusing on this to emphasize that topology is an extremely abstract topic. We have to really work to wrench ourselves free from our spatial intuition about numbers. We're talking about something completely different here. Analogizing to real numbers is helpful, but it's important to develop a further intuition of when our grade school intuition is helpful and when those intuitions might be limiting or misleading. The most important thing in learning math is in developing an understanding of the topic. When we start applying theorems by rote, we're on thin ice. So topology in particular is going to be an avalanche of definitions that we have to fit together against all of our better judgment. So we have to do two things at once: break down our old intuitions and build up new intuitions. So keep in mind that when we picture Cartesian coordinates, we're implying that there's an order on the sets, right? Because they get bigger as they go this way, they get bigger as they go that way. But the sets we're crossing here actually don't need to have an order at all, because sets themselves do not have an order. So we can cross any two sets, even without an order. Okay, so there's another problem with this definition. Can you see what it is? It assumes that we know what an ordered pair is, but we've in fact never defined what this even means. And this isn't just being pedantic, as we're going to see in a minute. In order to extend this definition to an arbitrary number of sets, we need to be rigorous about what an ordered pair is. So before we start building a definition of Cartesian products for an arbitrary collection of sets, let's just look at what an ordered pair is. So we can take an ordered pair as a primitive concept, the same as the notion of a set itself. Just define it and then leave it at that. And in fact, Rudin, that's how he does it. He never spends any time thinking about what an ordered pair is. You just assume everyone knows what an ordered pair is. But it can be given a definition in terms of the set operations that we've already talked about. So let's think about how to do that. What's the problem with an ordered pair? It's the order part. You can't just say an element from A and an element from B, because it's the order of the objects that matters, meaning that A comma B does not equal B comma A, right? So we can't just say the ordered pair has A and B. We need to know that A is first and B is second. So you might want to pause here for a second and see if you can think of a way that we can, using our set language, come up with a way of defining what an ordered pair is, so that A is first and B is second. Okay, well, so here's one way that this can be done. One definition in terms of set operations says that an ordered pair is a collection of sets with two elements, one that has one element and one that has two elements. If A does not equal B, then this definition says that the first coordinate of the ordered pair is defined to be the element belonging to both of these sets, and the second coordinate is the element belonging to only one of these sets. Because remember, again, there's no order inside this collection. We can't say that this is the first set in this collection and this is the second set in this collection. And then if A equals B, then the ordered pair AB is the collection containing only one set with the element A, because then AB equals AA equals A. So the first coordinate and the second coordinate both equal the element in this single set. So this is a clever solution to the problem. How do you add information about order to a set when sets don't have order. But looking at this bizarre formulation of an ordered pair, it's fair to say that most mathematicians think of an ordered pair as a primitive concept rather than thinking of it as a collection of sets, because this is just bizarre. But even if we go with this definition can't be extended in a simple way. If you're interested, try playing with this for a little bit. See if you can figure out a way to do this even for 3 elements. And remember, what do you do if A equals C or B equals C, or they all equal the same value, and so on. Okay, so let's move to a new page. Okay, so how are we going to define Cartesian products for an arbitrary collection of sets? In order to do this, we have to build several new concepts. Most importantly, we need to define a way to index the sets in the collection so that we can access the elements of a set in order. And this is different from what we did when we defined the real numbers, where we imposed an order relation on the elements of the set. In that situation, we simply defined a relationship, A is less than B, between every element of the real numbers, right? You take any 2 real numbers and either A is less than B or B is less than A, or they're equal. So this is the definition of how the elements inside the set relate to each other. That's not what we're doing here. Rather than defining an order relation between elements inside the set, we're imposing an order from the outside. Because remember, what we need here is that for any 2 elements, if it's A comma B, we say that A is first and B is second, but if it's B comma A, we say that B is first and A is second. That relationship is not a relationship between these 2 elements. It's an order that we impose on those 2 elements for a certain ordered pair. So we're going to do this with a function that specifies which element is first, second, and so on. So if we have a function that goes from a set 1 comma 2 to a set X, then you put in 1, you'd get 1 element, you put in 2, you get another element, right? So then that would make the ordered pair. So this will work because then if we had an ordered triple, for instance, then we could just do 1, 2, 3, and then 1 could point to 1 element, 2 to another element, and so on. But then there's already another problem with this. This only works when all the elements in the ordered pair or the triple or whatever are from the same set. But remember, what we said was, for a Cartesian product, A and B can be from different sets. They're not from the same set. But you can't define a function that goes from 1 set to 2 sets. That's just not how functions are defined. This doesn't work. So we're going to have to find a way to make it so that even if these are all from different sets, we can define a function that will return elements from all the different sets together. So that's an additional element that we're going to have to figure out here. Okay, so let's start by defining an indexing function. Let capital A be a non-empty collection of sets. An indexing function for A is a surjective function f from some set J called the index set to the collection A. The collection A, together with the indexing function f, is called an indexed family of sets. Surjective means that it covers A, meaning that some member of J maps to every element inside A. So every element of A is accessible from J. And now notice here, importantly, we are not talking about indexing the elements in an individual set. The indexing concept is about indexing a collection of sets. That's important to keep in mind. So I'm picturing this idea kind of like a slot machine or a combination lock, where each real has several values in it, and then the indexing function just tells you which real you're looking at. I want an element from real 1, an element from real 2, and so on. It doesn't return a value on the real, it just returns the wheel itself, the set that's at that position. Okay, so given alpha, an element of J, we will denote f at alpha by the symbol A alpha. So this A sub alpha is just shorthand for saying we're taking f at alpha. We'll denote the indexed family itself by this symbol, which is read the family of all A sub alpha as alpha ranges over J. And then sometimes we can just write A sub alpha without the J if it's obvious what the J is. So from here on, all of this symbology starts to get heavy. So try to make sure you let all of this stuff sink in. This thing represents a family of sets, which is indexed by J. And you know that we're talking about a collection of sets because the curly braces mean that this is a set, but the elements of this set are capital letters. That means that the elements are sets. So that means that this is a collection of sets. And now notice one more thing. Even though the function f is required to be surjective, it is not required to be injective. An injective, remember, means that for each value in the range, there's only one j that goes to that element. So we don't have to have that. It's entirely possible for a sub alpha and a sub beta to be the same set inside A, even though alpha does not equal beta. So one way that these indexing functions are used is to give a new notation for arbitrary unions and intersections of sets. This concept or notation is going to be used repeatedly in our study of topology. In fact, the notation that I'm going to present here is the reason that I felt these videos on basic set theory were necessary. These are the concepts that topology is based on, and it's important for us to be able to understand what these equations mean when we see them. They're very far from the algebra and calculus we learned in high school and college. Okay, so let the function f from J to the collection capital A be an indexing function for capital A. And then let A sub alpha denote f at alpha. Then we define the union of the A sub alphas with alpha an element of J as the set of all x such that x is an element of A sub alpha for at least one alpha in J. And the intersection of all of the A sub alphas is the set of all x such that x is an element of A sub alpha for all the alpha in J. So these are simply new notations for the general union and intersection that we defined last time. But you can see at once that since the indexing function is surjective, that this one equals the union of all of the elements in the collection A, and that this one equals the intersection of all the elements that are in the collection A. So there are two especially useful index sets. One is the set of all positive integers from 1 up to n, and the second is the set of all positive integers. For these index sets, we introduce some special notation. So if a collection of sets is indexed by the set 1 to n, then we can denote the indexed set as curly brace a1 comma dot 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 an, and we can denote the union and intersection this way as a1 union dot 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 union an and a1 intersect dot 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 intersect an. And then in the case where the index set is all the positive integers, then we can denote the indexed family by the symbol a1 a2 dot dot dot, and the union and intersection by a1 union a2 union dot 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 and a1 intersect a2 intersect dot dot dot. You could write the union this way for a finite set and with infinity for an infinite set, and then the intersection the same way. So note something here. This means the fact that we're looking at these counting sets as something special means that in our original definition, J does not need to have been countable at all or even ordered in any way. J doesn't have to even have an order on it. It's just that each element of J goes to an element in the collection of sets. But it doesn't have to be ordered and it doesn't have to be countable. Okay, next up, M tuples. Let M be a positive integer. Given a set X, we define an M tuple of elements of X to be a function from the set of positive integers up to M to X. If X is an M tuple, we often denote the value of X at I by the symbol X sub I rather than X of I and call it the ith coordinate of X. And we often denote the function X itself by the symbol parenthesis X1 dot 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 Xn. So this is weird stuff, but it's just an explicit way of defining tuples using set notation. We normally think of X sub I as the ith coordinate. So the number in the third place is the third coordinate. This kind of turns that on its head. In this situation, there's a separate function X for each point. You tell the function which coordinate you want, and it returns it. So if we have this 5 tuple, then you ask x what's the third coordinate. You pass 3 into x, and it returns 7. A different point in 5 space would have a different function x. And of course, these functions in another context would be vectors. So this is a very heavy explanation for a very simple concept, because we're used to just thinking of vectors as, this set of points, 5, 6, 7, 8, 9. Here we're saying, no, this is actually a function, and a different point in 5-dimensional space would have a different function, and so on. So these two functions, this tuple function x and the indexing function f, they both map one set onto another. But notice the differences between the tuple function and the indexing function. The indexing function maps a set onto a collection of sets, whereas x maps the set onto, this is a regular set of elements. And also notice that the tuple function requires the domain to be a subset of the natural numbers. And also, unlike the indexed function, x is not required to be surjective. X can be infinitely large, while the indexing function is just a few elements. So we have two mapping functions. There's one more step to make a Cartesian product. Okay, so now Cartesian products. Let A1 to AM be a family of sets indexed with the set of positive integers from 1 to m. Let x equal the union of A1 to AM. We define the Cartesian product of this indexed family to be the set of all m tuples of elements of x such that x sub I is an element of a sub I for each I. We denote this Cartesian product by the product symbol from 1 to m of a sub I, or a1 cross ... cross am. So we can see now the strangely roundabout course that we were required to take here. First, we defined an indexing function, which maps an indexing set J onto sets in a collection of sets, which was... Then we used this function to define arbitrary unions of sets. Then we said we can let J be a set of natural numbers from 1 to n. Then we defined another indexing function from the natural numbers from 1 to m into a set x to define an m tuple. Then finally, we've combined these two different index functions using the same domain to define the Cartesian product for an arbitrary number of sets. But look at how strange what we ended up with is. What we want to do here is take the Cartesian product of several sets, but we can't just say it's a set of m tuples, because an m tuple can only be defined for one set. So first we have to take the union of all those sets to make basically a giant blob of a set. It's a very strange thing. It's not complicated. It just leaves you with this strange lumpy monstrosity of a set with A1 over here, and A2 over here, and AM over down here, and so on. And this is the reason for the first thing we defined in this video, taking the union of an indexed family of sets. We had to start by defining what we mean by this before we could use it to define X, so that we have one big set from which to define our M tuple. Now with all that set up, we can finally define the Cartesian product. Again, you could think of this as a slot machine or a combination lock. Each set A sub I is one of the reals in the lock, and each M tuple is one of the combinations for the lock. The set X is all of the numbers on all of the reals of the lock put together. I think this is amazing. If you don't think hard about it, an m-dimensional tuple is completely easy to understand. But if you really try to build what it means from scratch, there was a lot we had to go through to get from, quote, a set is a collection of objects, to a Cartesian product is this. It's very interesting. So now with all this in mind, we can go back and define an ordered pair as a 2 tuple, which we kind of hinted at the beginning of the video. And then this would just be denoted by the symbol x1 comma x2, right? And we're right back where we started. Okay, that's the definition of a finite dimensional Cartesian product. Insanely, it's also possible to define an infinite dimensional Cartesian product as well, which are called omega tuples. So, omega tuples. Given a set X, we define an omega tuple of elements of X to be a function X from the positive integers to the set X. We also call such a function a sequence or an infinite sequence of elements of X. If X is an omega tuple, we often denote the value of X at I by X sub I rather than X of I and call it the ith coordinate of X. We denote X itself by the symbol x1, x2, ... or X sub n for all n in the positive integers. So isn't that interesting? This says that we can think of an infinite sequence of objects as an infinite tuple of values. In other words, an infinite sequence of values can be thought of as a point in infinite dimensional space. That will really warp your brain. We've been talking about limits, right? This limit is a sequence of numbers that approach zero as x approaches infinity. We can think of that sequence instead as a single point in infinite dimensional space. It's so weird and interesting. That is a drastic change in the point of view of what a limit is and what an infinite sequence is and what dimensional space is. We'll have to see where this takes us. Okay, so now with omega tuples in hand, we can define the Cartesian product of an infinite number of sets. So let A be a family of sets, A1, A2, ... indexed with positive integers. Let X be the union of the sets in this family. The Cartesian product of this indexed family of sets is defined to be the set of all omega tuples of elements of X such that X sub I is an element of A sub I for each I. It's denoted by the product of all A sub I where I is a positive integer, or A1 cross A2 cross ... So notice again that there are two separate functions at work here. The first is the function x, which represents the omega tuple and is indexed by the positive integers. The second is this infinite family of sets, and that collection is also indexed by the positive integers. This is really esoteric and obscure. All we're doing is defining rigorously using set notation concepts that we've already been talking about naturally. A 3D vector looks like this, and so on. It's weird, and something we haven't talked about before, to think of an infinite dimensional vector or an infinite dimensional Euclidean space, but now we can. So one last thing here. Nothing in these definitions require these A sets to be different from one another. They may all equal the same set. In that case, the Cartesian product from A1 to AM is just the set of all M tuples of the set X, which we denote by X raised to the M. Similarly, the product A1, A2, ... would just be the set of all omega tuples of elements of X, which we denote by X to the omega. So we use M and N to denote finite dimensional tuples and omega to denote infinite dimensional tuples. Later on, we will define the Cartesian product for an arbitrary indexed family of sets, meaning that we can take the Cartesian product of an uncountably infinite dimensional space. But we'll get to that later.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.